we are going to see the hysteresis loss. Hysteresis loss is an important thing. Here the coil is connected to the battery and key. When the battery is connected to the coil, it will become magnet. It changes from an ordinary conductor to a magnet. So using that, we are going to study the magnetizing property and how the flux density and the magnetizing field. We are placing the ferromagnetic material inside the coil. So when that we are going to draw the graph between the magnetizing field and the flux density. Okay, H is a magnetizing field. How we are going to magnetize the ordinary material into magnetic material. B is the flux density, how much it can retain the magnetic field. Now you see that when the switch is connected, the current flow through the coil, it will become a magnet. So you know that the current flowing through the coil, inside that coil we place the material that will become a magnet. That one pole is north, another one pole is south. So when you draw the graph, so magnetization and B, so using this experiment you can draw the graph. When you draw the graph means it can be increases from O to that P, that is see in your book. So this is the magnetization. So when you are magnetizing that material, so magnetizing increases, that field also increases. It's a maximum value at times. Okay. Now we can decrease the current. So initially we are applying the current. Now we decreasing that current. When you are decreasing the current, we are demagnetizing that material. When you are decreasing the current, that flow, that material is demagnetized, but it is not comes to zero. It has some value. See that from point O to that point, that is called retentivity or remanence. That retaining the small part. So the magnitude of the reverse magnetic field, which residual magnetization of the material vanishes, is called coercivity. First is called residual magnetization. Present in the specimen is called remanence or rigidity. It is defined as the ability of the material to retain the magnetism in the even magnetic field is vanishes. Then last thing, see that the magnitude of the reverse magnetic field for which the residual magnetization of the material vanishes is called coercivity. See, after removing that, we are applying the opposite direction current. It is decreases to zero. It has some value. That value is called coercivity. Okay, reverse magnetization field for which the residual magnetization of the material vanishes is called its coercivity. Again, we are increasing up to attain the saturation level. The negative direction is increases. So it reaches the maximum saturation in opposite direction. So it came in the opposite direction, right? So opposite direction, it is increases in a maximum. Then we are increasing in a decreases the current, but in a opposite direction. So what will happen? See, again that current is decreases. That means it will decreases from saturation region to in a negative direction. So it reaches the from saturation in opposite side to the magnetized field in a opposite direction. So it attains the point G. From F to G. After reaching that point, again we are increasing the current in a opposite direction. So we are increasing in a opposite direction. When increasing the opposite direction, so what will happen? We are magnetizing that. So that magnetizing increases means the magnetic flux density also increases. Then again you are increasing that current means that flux density also increases and magnetizing also increases. It reaches the maximum value of saturation. So saturation means initially it got the same value, that point is called. So the entire cycle, the magnetic induction B lags behind the magnetizing field H. This phenomenon of lagging of magnetic induction behind the magnetizing field is called hysteresis. So hysteresis loss, you can write it that delta E equal to integral of closed integral of H dot dB. That is explained by that hysteresis loss. So using that we can find out hard and soft magnetic material. Suppose that graph is a very large area, that is called hard magnetic material. That large, it's a very small area means that is soft magnetic material. So using that hysteresis, that loop, we can find out that hard and the soft materials. And the application of hydrolysis loop is using that we can produce the permanent magnets and the electromagnets and core of the transformers. So using the coercivity, permittivity, susceptibility, energy loss during the cycle of magnetization for each ferromagnetic material, the study of hydrolysis loop will help us to select the suitable material for the purpose. First one, we can use the permanent magnet. Permanent magnets with high resistivity, high coercivity, high permeability are suitable for making permanent magnets. So எல்லா வேல்யூ ஹையா இருந்துச்சு அப்படின்னா நம்ம எதுக்காக யூஸ் பண்ணலாம் அப்படின்னா permanent magnetic யூஸ் பண்ணலாம். Electromagnets are high initial permeability, low resistivity, low coercivity and thin hydrolysis loop with smaller area preferred make to electromagnets. So அந்த வேல்யூல ஸ்மாலா இருந்துச்சு அப்படின்னா ஈஸியா அதோட மேக்னெட்டிக் ப்ராப்பர்ட்டியை லாஸ் பண்ணிடும். அதை வந்து எதுக்காக யூஸ் பண்ணலாம் அப்படின்னா electromagnets. Then finally, its example for the electromagnets are soft iron and mu metal. It's made up of nickel iron alloy. Finally, it's the core of the transformers. So core that is made up of soft iron that is placed, it's a high initial permeability with large magnetic induction and thin hydrolysis loop area are needed to design the transformer cores. This is used in the transformers. So transformer அப்படிங்கிறது என்ன fourth lessonல பார்ப்போம். அதுல நம்ம யூஸ் பண்றது இந்த hydrolysis loop தான். So up to this we completed that classification of the materials. Okay. So next we are going to see that these are all the difference between the dia, para and ferromagnetic materials. So diamagnetic substance which are feebly repelled magnet and attracted magnet, then finally attracted magnet, and what are all the materials? It has the dia, para and ferro. See how the placed in a magnetic field lines of force. And next thing is placed on non-uniform magnetic material, how it is direction, weaker to stronger or stronger to weaker. Using that we can classify that. So these are all the things. Diamagnetic metal equivalent taken into watch glass. These are all the examples. It is not necessary for you. That is finally it's a Curie's law. Hydrolysis loop, that is a closed area. So now we are going to see the magnetic effect of current. So magnetic effect of current. So magnetic effect of current is a very, very important thing. Initially, I told you that scientist named Hans Christian Oster discovered that when the current flow through the wire, nearby the magnetic compass shows the deflection. After that electricity and magnetism become a single subject, that is electromagnetism. That's a very important observation observed by the Hans Christian Oster. So now we are going to see the Hans Christian Oster. From that experiment we are going to see that one experiment. So an electric current produces magnetic effect. The space around the conductor is called magnetic field or simply magnetic field. ஒரு கண்டக்டர் வழியா கரண்ட்டை ஃப்ளோ பண்ணோம் அப்படின்னா அந்த கண்டக்டரை சுற்றி ஒரு மேக்னெட்டிக் ஃபீல்டு இருக்கும். ஸோ தட் இஸ் அ மேக்னெட்டிக் எஃபெக்ட் ஆஃப் கரண்ட். Oster's experiment. When current was allowed to flow through a wire placed a parallel axis of magnetic needle kept directly below the wire, the needle was found to deflect from its normal position. ஸோ நார்மலாக ஒரு பொசிஷனில் வச்சுருக்கோம், கரண்ட் ஃப்ளோ ஆகுது, அப்போ எந்த டைரக்ஷனில் டிஃப்ளெக்ட் ஆகும் அப்படிங்கிறத வச்சு ஒரு எக்ஸ்பிளைன். Next thing is the Maxwell right hand corkscrew rule and right hand thumb rule is here. These rules are used to find the direction of flow of current and magnetic field. So now we are going to see the first one, right hand thumb rule. First one, we have seen that magnetic around the straight conductor, Maxwell corkscrew rule. See that Maxwell corkscrew rule. So now you can see that you imagine that right hand corkscrew rule lying with the axis of coincident with the current carrying wire. There is a current carrying wire, okay, that is inserted into a cork. The direction indicates the flow of current. The direction means it is moving from left to right. See, the straight line indicates the direction of the current. That rotation of the hand will indicate the magnetic lines of force. So the rotation of that hand indicates the magnetic lines of force, but it is moving in a straight line, that is called the direction of current. Okay, this is called Maxwell right hand corkscrew rule. So the screw is moving in a advance, that is the direction of current. The rotation, that finger rotation, that rotation is called magnetic lines of force. Next one, magnetic field around a straight conductor. This is a right hand thumb rule. So right hand thumb rule, it will give the direction of magnetic field. So see that if we hold the current carrying conductor in our right hand such that the thumb points the direction of the current flow, the finger encircling the wire points in the direction of magnetic field line produced. So see that right hand is such that thumb points the direction of the flow of current. Thumb finger, that is a conductor, thumb finger indicates the direction of flow of current. Okay. So thumb finger indicates the direction of current. Our conductor la நம்ம ஸ்கிரீன்ல பாக்குறீங்கன்னா கீழ இருந்து மேல current போறதா வச்சுக்கலாம். So the thumb finger indicates the direction of current. And the thumb finger indicates the direction of flow of current. It's moving in a upward direction in the conductor in the image. So that fingers around the conductor. So the fingers around the conductor indicates the direction of magnetic field. So thumb finger is the direction of flow of current. So the upward direction. The finger indicates the direction of magnetic field lines. Magnetic field lines. It is producing the magnetic field lines. Okay, it's called right hand thumb rule. Okay, up to this we complete the session.